Hello and welcome everyone to a special SETI Live. We are coming to you today on Giving Tuesday, which has become an international day of philanthropy. The SETI Institute has a special challenge today for viewers and followers. If we receive 300 donations today, our guest Steve Trimberger will make an additional $10,000 donation to the organization. This is a great opportunity to make your gift go further by helping the SETI Institute meet this challenge. And right now, as we start this live stream, we're only 116 donors away. So I'm going to go ahead and get started and let's do the thing. Let me know where you're watching from and tell us, save your questions for a little bit later. We're going to talk about a really cool topic. So you've read it in many headlines. Researchers detect a mysterious signal from outer space. What does that really mean? And how do scientists determine if a signal is from ET or a natural phenomenon? Joining me today is Dr. Wael Farah, a researcher here at the SETI Institute's Allen Telescope Array. And we're going to talk about recent signals of interest and how the scientific community studies them. And again, also with me today is Steve Trimberger, who is being a very generous donor today and has set up this challenge for Giving Tuesday. So I want to welcome you both to the chat today. To live stream. Here you are on Facebook and Twitter and Twitch and YouTube. And Steve, tell us about this challenge and who you are and why you have set this up. What motivated you to set this challenge out today? And don't forget to unmute both of you.
Take care of that. Thank you, Beth. So I'm just like, I think a lot of people on this call, I'm just very interested in space and in the search for extraterrestrial intelligence. That's what I'm interested in. It's very exciting. I talk about it as one of those activities or one of those endeavors that we as humans can do that's sort of bigger than our everyday lives. I mean, humans are made for more than just who won a sporting event over the weekend or which politicians are posturing or bickering with each other. This is one of those opportunities to be bigger than just ourselves. The universe is a marvelous, wonderful place. And there's just a very exciting activity here. Just contemplating, searching for a life, intelligent life in the universe I just find that thrilling. About the challenge, my wish was to share this excitement. And so the challenge is tied to the number of people who are going to join with us and share that excitement. That's what I want to have happen. That's what's thrilling to me. And then, if 300 or hopefully more than 300 people finish the day, and then somebody says, "What did you do today?" And you say, "I supported searching for intelligent life in the universe." That's where you want to be. That's the sense of excitement that I want to get everybody, the sense of being bigger than just the day-to-day things.
So how did you end up involved with the SETI Institute specifically?
My involvement went back many, many years. I was in the electronics industry, and I got a this was long before all this social media stuff. I got an actual letter in the mail, and someone saying, "Oh, well, we're looking for extraterrestrial life, and we would like some free computer chips." And so I didn't know who this was, and so I did a little bit of homework and found out, oh yeah, Dan Wertheimer at University of California, Berkeley is a pretty good guy. And so, yeah, I should do that. And but that just got me in contact with in real personal contact with this larger community. The building equipment and radio telescopes and the excitement is certainly there. It's a long vision, and so that's how I got into it, and then it's just been building ever since.
Well, we're very grateful that you're here, and it's not every day you get to say to someone, "I really hope we get to make you write a $10,000 check today." So,
I would be delighted to do that, but it's not up to me. It's up to right now the 184 that are already on board and 116 that are out there. And come on, get some of Steve's money over to the SETI Institute.
all right, so we're going to put the links for where you can make that donation in our various chats, and you can also find it right on our website at seti.org. We have viewers checking in from Ohio, Louisiana, North Carolina, Maine, Kentucky, Oklahoma, Wisconsin, Florida. And outside of the United States, we have Honduras and Australia. So we're getting a pretty nice global audience. So welcome, everybody. And now I want to talk to Wael. So Wael, we're here really to talk about some of the signals that have been discovered over the past few years. I know you've been involved in quite a few of these projects so far. I think there's 3 that we can really kind of pinpoint right now that we've talked about before. What's the first one you want to talk about today?
The signals that I would like to talk about are in general fast radio bursts. This is one of the radio bursts that I totally enjoy talking about. We can also talk about BLC1, which is the Breakthrough Listen Candidate one.
Right.
Candidate, which was detected quite recently and was actually published a month ago in one of the top astronomy journals. We can talk about all of this. We can talk about also the role of the Allen Telescope Array, which is on this slide, in the search for extraterrestrial intelligence and the search for such signals.
Okay, so let's start at the beginning. We have a radio telescope array. Mm-hmm. What are we using it to do? What is it actually doing?
Right. So in radio astronomy in general, we have kind of 2 paradigms as to how we can do our science. We can either use a single radio dish, so a big telescope. Of course, the bigger the radius of the telescope is, the more light that we can collect, and the more sensitive we are. So we can go towards the route of a single big dish, or we can use interferometers, which are a collection of smaller dishes collectively working together in such a way to synthesize or to hypothetically create a large dish. In terms of interferometers, like the Allen Telescope Array that you see behind me, we use the instrument in multiple ways, and one of the most common ways to use an interferometer is to combine the signals from every single dish or from every single element in such a way that we maximize the sensitivity from a particular location in the sky. So this is one of the ways we can use interferometers. Also, another way we can use interferometers, because interferometers have smaller radii compared to big dishes. It means that we have a bigger field of view on the sky. So generally, if you want the area that we are sensitive to using any telescope is inversely proportional to the radius of the telescope. So as the radius of the telescope decreases, we have a bigger, if you want, image on the sky that we can create, or a bigger sensitivity on the sky, or a bigger area that we can record on the sky. And so we can use the Allen Telescope Array in such a mode where we can use the big field of view of such a smaller radius instrument to survey the sky. So these are the couple of ways that we can use an interferometer.
So this is sort of the difference between, say, a big radio dish like Arecibo was, and then what we have are our 42 sort of scattered dishes that you can move around and aim individually if you need to.
Exactly. Yes.
Okay. So some people like to, this comes up frequently. It's sort of a frequently asked question or a frequently made comment. When we talk about observing things in radio, we're not talking about putting on headphones like these, sitting on the hood of a car and listening to radio waves, right? We're actually talking about imagery, essentially, just not invisible light.
Exactly. Radio waves are electromagnetic, are part of the electromagnetic spectrum. They are nothing special compared, or they're non-special compared to the light that our eyes are sensitive to. It's pretty much the same thing. It's just that radio waves have longer wavelengths, hence smaller. Longer wavelength means less energy, basically. So radio waves are less energetic compared to higher frequency or smaller wavelength light. And radio telescopes also are not really special in such a way that all they do is they just collect as much as they can radio waves, and then they focus it onto a feed or a sensor, essentially at the focus of the instrument, and then that feed just senses the electromagnetic light. So basically, it's the same basic concept as a optical telescope that many amateur astronomers, probably a lot in our on our audience use. It's basically the same concept, but slightly different hardware.
Okay, so walk me through what the process is for detecting a signal, which sounds far more dramatic than I think it really ends up being, correct?
Depending on how you define dramatic. In terms of complexity, I would say it's pretty dramatic, especially when it comes to instruments like the Allen Telescope Array, when such an instrument, world-class instruments are really complicated to deal with. So yeah, let's start our journey. So let's see. You see my hand? Yeah. So we've got our instrument somewhere here. We've got some light that shines, or light that is being received by the instrument, gets picked up by the feed. Oh my gosh, this is inverse. So so we've got our sensor somewhere in the middle there that picks up the signal, and the electromagnetic wave here. Apologies for all the jargon. Basically couples in with the feed, and so this generates basically a voltage, right? Just a small, tiny little voltage. And this signal gets sent in analog all the way to a signal processing room. Inside the signal processing room, we have multiple devices that we use to basically tune to what frequency we want to listen to. Same as pretty much really close to what a radio in our cars, the analog ones used to do, but of course, a bit more complicated. And but basically, yeah, we just tune in for the frequency. So we just tune in what frequency we want to listen to. And then we tune in what volume we need to listen to, right? Like we cannot really blast our, quote unquote speakers, and we cannot really have our volume really low. So we have to like put our signal in such a way that we can hear it audibly. Of course, it's not audible anymore, and this is not an audible instrument per se. But I'm making this analogy. But we have to tune it in such a way that the signal is not really oversaturating our devices down the track. And then once these are set, the data gets transferred or gets converted from analog, basically just voltages in analog, to digital. Once that is done, we tend to do, once the signal is in digital, at that point, I would say the magic happens in such a way that we can use this digital signal to do many radio astronomy operations. One of the simplest one is to multiply all the antennas together. This will create something called a cross-correlation product, and then we can use that to make an image of the sky. This is one thing we can do. If we were to search for extraterrestrials, what we need to do for extraterrestrial intelligence, what we need to do is we take this digital signal and we pass it through a what we call a spectrograph or a spectrogram. And this channelizes the data. So we have to go down to a frequency resolution of a really small value, around a few hertz. Once the data is in such a format, it then passes through what we call a D-Doppler or Doppler accelerated search. You know, I can talk about this basically. I'm throwing all of these terms around, but please stop me at some point, Beth.
Okay, so you've aimed your telescope at the sky. You've processed your data down into something usable. What makes you say we found something interesting?
Now, that is another complicated problem on its own. And that is because we are, I'd like to say that always, but we are scientists. And when I say we are scientists, we follow the scientific method. And what I mean by that is, if we were to find something that appears to be interesting, we have to at least make sure that this observation is repeatable. And we have to make sure that there's nothing, we are not fooling ourselves with what we're seeing. We have to make sure that what we're seeing is legit. And this passes through a rigorous set of procedures in order to get to that point. And that is from very basic, looking at what interferer signals might be around, let's say, the telescope site. If there were any satellites in the field of view when the telescope was recording.
If someone leaves a microwave open.
If someone leaves their phone on,
Right.
someone leaves their phone on and they are in the car and the car is driving 60 miles an hour down across the tunnel, all of this goes into the equation. But we can talk a lot about these details, but basically what I can summarize is that this goes through a rigorous process so that we are able to wipe out any terrestrial or human-made signals from something that is actually astrophysical.
Okay, I want to talk to you some more about some of these possible signals that we touched on very briefly, but I'm going to welcome some people in. We have people now watching from Washington, New York, and Georgia, as well as Germany, Wales, England, and Canada. So again, a very nice global audience going on here. Just as a reminder, today is Giving Tuesday. We are raising money for the SETI Institute. Federal funding for SETI research itself is pretty limited. So supporters like those of you viewing right now are what keep us going, what makes the Allen Telescope Array continue to be able to look for signs of intelligent life out there. And Giving Tuesday is all about giving back and supporting organizations and missions that you care about. So here, our mission is to understand the nature and prevalence of life in the universe. So if you're also curious about that and you wonder whether or not we're alone here in this great big cosmos, maybe make a donation so we can keep looking. All right, Wael, let's talk about the fast radio burst discovery. First, and I almost hesitate to ask this question, but what is a fast radio burst and why do we care?
Okay, so I can describe this, or I can answer this question in a couple of ways. I can answer it from a practical side of view, or from an observational side of view, or point of view, or I can answer it from a more theoretical point of view. From the practical, yes.
Probably go with the practical.
I'll go with the practical. Well, I mean, let's go with the theoretical. From the theoretical side of view, we have no clue. That's my answer. That's basically my answer. We still have no clue.
I was expecting that one to be the longer answer.
Right? I'm no theorist myself, Beth, so I won't put myself in this go through this wormhole. But so basically, yes, we do not know what fast radio bursts are as of yet. There are a lot of theories that can explain some of the observed properties of fast radio bursts, but there is still no consensus as to what these objects are.
Mhm.
On the practical side of things, fast radio bursts are transients. And what I mean by transients are, it's an object that appears somewhere in the sky and then disappears, right? It just flashes. A transient is a flash, right? It's a flash in radio waves. This is called a fast radio burst. It's a flash in radio wave. And it has the characteristic that it is coming from outside our galaxy. And we have proved that, right? We have proved that these objects or these signals are coming from outside our galaxy. And if something's coming from outside our galaxy, it's really far away from us, which means that it has to be really energetic to emit this, it must be really luminous for its signal to actually be received by us and be detected by us. So these are fast radio bursts. Some of them repeat, some of them don't. Some of them appear to have some fine spectral structure, some fine temporal structure. Some look alike, some have, but yeah, they are millisecond wide, right? I'm talking about a millisecond that just goes, on off and then it disappears. So that's a story of fast radio bursts.
Okay. Quick second. I want to thank Chris Walker for the donation, and also I want to thank Michael Harrington for the stars on Facebook. So thank you so much. Your stars, your super chats, and your bits all help support us. So thank you everybody. Okay, so why are fast radio bursts interesting when it comes to SETI?
So fast radio bursts are interesting in general. They do have a lot of potential for us to use in order to study our universe and to learn more about the universe. They are interesting per se when it comes to SETI because detecting a fast radio burst with an instrument basically proves that the instrument is working in its, I would say, it's working properly. It's working the way it's intended to be working, or it's functioning the way it's intended to be functioning. And I say that because finding a fast radio burst is kind of hard. And to explain more, everything has to be in kind of a perfect working order, from where we're pointing on the sky to how we digitize our signal, to how simple things like what frequency we're observing, how good our timing is, right? We've got a clock at the instrument that sort of tells time to all of the antennas, and if we are not careful enough about how we combine the signal from the antennas, we just end up with pretty much garbage. And so this has to be also in perfect working order. And so basically, when it comes to SETI, finding an FRB is pretty important because it tells us that a telescope is actually working. Also, I'd like to add another thing, is that searching for an FRB is sort of similar to searching for SETI or doing SETI. An FRB is dispersed in frequency. So in other words, as the radio wave from an FRB or fast radio burst propagates through the intergalactic and interstellar medium, it undergoes something called dispersion. Long story short, as the signal arrives to the Earth, the lower frequency of light gets delayed compared to the higher frequency of light, following a curved relation.
Okay.
But that's called dispersion. When it comes to SETI, because a narrowband emitter on a different planet that is has a radial velocity or is moving away or towards the Earth undergoes a Doppler shift, means that the signal that would appear here on Earth might have a might be Doppler shifted. Basically, it's like an ambulance passing down the road. The higher frequencies appear, or the frequency of light changes as a function of time. So what I'm trying to say is it's a similar search technique. It's a similar search methods that we use in both sciences. And this is great because there's a lot of transfer of knowledge between doing SETI and between doing FRB science.
So to our viewers, one of the things that you heard him talk about was that the telescope has to be in working order. We have to make sure that it's working. And in order to do that, one of the things that we do is we raise money to make improvements to the Allen Telescope Array, as well as pay for the research that we're doing on that. So since today is Giving Tuesday and our goal is 300 donations today so that we can get an additional $10,000 from our generous guest, Steve Trimberger, we would like to see if we can hit 200 during SETI Live, which means we only need 11 people to go to our link and make donations. And I totally feel like I am on PBS right now, but it is really important. This is how we do SETI research because we are very limited in the government funding that we get for this kind of thing. All right, Wael, BLC1. It's kind of one of those big news things. Turned out to not be the big news we all wanted it to be. But how does this process work? You get what? Can you walk us through that? You work on Breakthrough Listen a bit. So what was this like?
Yeah, I do collaborate with a lot of Breakthrough Listen researchers, and I was sort of on the insider when it comes to BLC1. But I can sort of summarize how things have propagated and how things went about. So the way Breakthrough Listen performs observation using big dishes, which is, for example, the Parkes radio telescope, which was used for the detection of BLC1, is that we follow this rigor. We follow this this smart way to find whether a signal is actually coming from a specific location on the sky or not. And this is called an on-off cadence. So what we do is that, let's say we want to observe a star, let's say a Proxima Centauri. Okay. We take the Parkes telescope, we point it at the source, we record for 5 minutes, whatever, we move away from the source, and then we record for an equal amount of time. And then we go back on the source and we record again. Now, if a signal is actually coming from Proxima Centauri, it would only appear in the on observations, right? Mm-hmm. And that's fairly, this is just following the basic laws of radio.
It seems like a very obvious thing to say. If it's coming from there, we only observe it when we're looking at the thing.
Exactly.
Okay.
And this is what made BLC1 interesting, because when researchers went and looked at the off observation, turns out that the signal is not appearing in the off observation. It was only detected in the on observation. And this sparked a lot of interest because this is exactly what we're searching for, right? Our algorithms did what they're supposed to do in the sense that they detected a signal that we classified as interesting, right? Mm-hmm. Now, this is not the only thing we have to do. There's a lot of things we have to look into, go back into archival data, look through, do a rigorous check as to whether the signal is actually real. Which was the case in BLC1. It turns out that there were a lot of other signals that were detected at other places in the sky that were really similar to BLC1, but that only appeared when we looked really deep into what was going on. On the surface, when it comes to our algorithms, the algorithms did exactly what they were supposed to do, and they provided us with an interesting candidate that we dubbed BLC1.
All right. Well, I want to thank Tony Davis for a donation. Thank you so much. And I'm going to start to take some audience questions. So feel free to go ahead and put those in the various chats, and my colleagues will be posting them to me. So I'm going to start going through them. This question is from Lionel. What or where is all of the processing power that works on the signals from the ATA, and what upgrades would you like to make to enhance your search?
Okay, so most of the processing power is on site. So we have something called a building called the signal processing room, where all of the beefy machines are actually in there. So all of the machines that servers, computers, and electronic boards that do most of the heavy lifting. And the reason we have to place them on site is that the data rate, literally the amount of data that the telescope pumps out is ridiculously high. I'm talking about 100 gigabytes per second for the technically oriented people. I mean, this is a lot. We cannot just send it through network, send the data through the network, and some server on the other side of the planet can pick it up. And so this is basically the answer is on site, at least for the first stage processing. This is on site. And I guess you asked for the upgrades.
Yeah, what upgrades would you like to make to enhance your search?
More processing power, that's for sure. SETI is a processing thirsty science, right, because we're really not, we know what we're trying to search for, but also not really. Like there's a lot of phase space or a lot of variables that we can sort of tweak and knob to change our search a bit, and this means that we have to search all of this phase space. And so more processing power, the merrier. And following Moore's law, every 2 years we get better processing power. I mean, this kind of, but yeah, more processing power. That's the short answer.
All right. Thank you to Kat Norris for the donation. You mentioned looking back at previous data, and that comes up with a question that someone else has asked. Do you ever correlate against a previous data set for the same sky location to look for the same signal below the noise floor?
Absolutely, absolutely. This is one of the techniques that we follow. So usually we have this threshold that we colloquially call the signal to noise threshold. It's basically an empirical value that we place on our candidates. Just because we have a limited number of eyes to look at candidates and the limited computational power to do what we really want to do. So basically, we only look at stuff that are above this threshold. But if we happen to detect something interesting, we can go back to archival data and look at this specific region, at really this specific time, maybe this specific frequency, at things that have lower signal to noise threshold, because the amount of candidates are suddenly so much lower to look at because we know exactly where we're trying to search. So yes, that's one of our best ways to actually confirm a candidate. That's one of the ways we do it.
Great. We have, wow. Thank you to, we got 2 donations on YouTube. One of them is from Andre. Thank you so much. Thank you to Klaus Altvater, who sent 1,000 stars on Facebook. Thank you to Carol, who also sent stars. Thank you to Chris McDonald, who sent another 1,000 stars. You are all so appreciated. And we apparently only need one more donation to hit that 200 mark before we wrap things up here. I do have one more audience question. Actually, I have a couple. So Ricky asks, how much of the sky do you look at and have you covered?
I see. So that's a brilliant question. We can, I can answer this question in a couple of ways. Statistically speaking, the more sky we can observe, the better. So if we literally search the entire sky, we're better off to do a better search, obviously. If you want to be slightly more clever as to how much time we spend on a particular region on the sky rather than spreading things equally, the better way to do it is to target regions of the sky where there are more planets or more chances that we can have a planet in our line of sight. And that mainly leads us to searching more towards the galactic center or the galactic disk, where more stars, hence more planets, are available. Yeah, and at the ATA, we've done a survey over the summer of the galactic center, and so we've done a tiling of the galactic center, a few degrees in each direction from the galactic center to do SETI. So this is one of the ways. Yeah.
Wow, that sounds promising and exciting. Referring back to our discussion about fast radio bursts, does the frequency of the fast radio burst give a hint as to its origin? And is there a lot of variation in the frequency of the FRBs?
Oh, interesting. The frequency of the FRB basically. Okay, let's put it this way. Some FRBs appear to be brighter at certain frequencies compared to others. While this might not directly hint to their origin, well, at least if you're talking about origin as in their emission mechanism, then this is probably a yes. If that's what is meant by origin, that's probably yes. I would say
I think so.
Yeah, then absolutely. Yes. And is there a lot of variation, I think, in frequency? Yes. Some FRBs appear to be more bright at lower frequencies. Some FRBs appear to be more bright at higher frequencies. Some repeating FRBs, for example, they repeat over a cycle of 16 days. One of the FRBs repeats at the cycle of 16 days. And then within the 16 days, there's a 5-day period where there's an enhanced, statistically enhanced, or within those 5 days, there's an increased chance to emit an FRB. And it turns out that within those 5 days, the early, depending on the day, it might emit at different frequencies. So something's going on, but the short answer is yes, hopefully.
Thank you to Dolores for sending 99 stars on Facebook. So appreciated. You guys are amazing. I think we're quite a bit past a half an hour now, so I'm gonna wrap things up. Wael, is there anything else you wanted me to ask you that I haven't asked you?
Well, that's putting on the spot there, Beth.
I'm sorry. I did promise beforehand this would not be a dissertation defense. Someone is asking on Twitch, what do you have a personal theory of what fast radio bursts are caused by?
Well, when I first started my PhD, I would have loved that they were black holes colliding with each other, because that's just the coolest thing I've seen, right? So 2 black holes deciding to bump into each other and, create one of the biggest explosions in the universe and emit an FRB. It turns out that this is not really the case, because we have evidence against that. But I personally think that FRBs are emitted by a type of object called a magnetar, and the magnetar is a neutron star that holds a really large magnetic field. And so the snapping of the magnetic field lines and the energy that is just held by the magnetic field reservoir is enough to generate FRBs. And so that's probably, I would say, my bet goes there, and my hope actually goes there too. So,
well, I hope that we figure that out while you and I are still around to enjoy the answer. All right. Thank you, everybody, for tuning in. I have good news. We made it to 205 donations. So thank you so much. Please consider making a gift if you haven't already. You can donate through the posts for these various streams. You can donate through the link that we've shared in the comments. We only need another 95 donors today. And Steve Trimberger, who is still here, and he can turn on his camera and say thank you as well. He will give us $10,000 if we reach that 300 donation goal, and we are well on our way there. So Steve, any final thoughts on Giving Tuesday?
Well, I'm real excited to see the progress and the progress we made just in the last half hour, 45 minutes. I definitely want to thank everybody and welcome you, join us on this great time of discovery. This is totally a totally exciting time.
All right. Thank you so much, Steve. If you are watching, thank you for being here, for spending some of your time with us. Thank you for donating. All those donations are incredibly helpful. If you are on YouTube, please don't forget to subscribe to our channel and throw us a like. Share us out with your friends. Help people find the SETI Institute and the science that we do and the outreach that we put together. I enjoy doing all of this so much for all of you, and I'm happy to be on camera talking to Wael, and this has been fantastic. And I could go on for a while while longer. I have like another 20 questions for a while just popping into my head. So we'll have to do this again and get some more information out there. So thank you, Steve, for the challenge and for being here today. And thank you, Wael, for joining us and answering all of these questions. And everybody have a fabulous rest of the day wherever you are in the world.